In electrical service installations, it is crucial to adhere to proper grounding and bonding practices to ensure safety and code compliance. The question of whether service grounds must be attached to the service bus or if it is permissible to attach a lug to the enclosure, often referred to as the can, is a common one. According to electrical codes, the service neutral must be connected to the service bus where the service entrance conductors terminate. However, the connection of grounding conductors and bonding wires involves a specific approach. Do not mount the lug to the neutral bus where the other bonding straps for the panel are located, as this would be improper. The lug must be connected to the grounding bus where the grounding system conductor is connected. All bonding wires also belong on that same bus bar, and that grounding bus bar must be connected to the neutral bus bar with a screw. This arrangement ensures a proper grounding path and minimizes the risk of electrical shock or equipment damage. It is important to distinguish between the neutral bus and the grounding bus within the service panel. The neutral bus is where the neutral conductors from the utility service are terminated, while the grounding bus is dedicated to connecting grounding conductors and bonding wires. Connecting the service neutral to the service bus is a fundamental requirement, as it establishes the reference point for the electrical system. This connection ensures that the neutral conductor is properly grounded, which is essential for the proper functioning of overcurrent protection devices. The grounding bus, on the other hand, serves as the central point for connecting all grounding conductors and bonding wires. This includes the grounding electrode conductor, which connects the grounding system to a grounding electrode, such as a ground rod or water pipe. It also includes bonding wires, which connect non-current carrying metal parts of electrical equipment and systems to the grounding bus. By connecting all grounding conductors and bonding wires to the grounding bus, a low impedance path is created for fault currents to flow back to the source. This allows overcurrent protection devices to quickly trip and de-energize the circuit in the event of a ground fault. The connection between the grounding bus and the neutral bus is typically made with a bonding screw or strap. This connection ensures that the grounding system is effectively bonded to the neutral conductor, which is essential for minimizing voltage differences between the grounding system and the neutral conductor. The location of this bonding connection is critical. It should be made at the service entrance, typically within the main service panel. This ensures that the entire electrical system is properly grounded and bonded. It is important to note that the specific requirements for grounding and bonding can vary depending on the electrical code in effect in your jurisdiction. The National Electrical Code, or NEC, provides comprehensive guidance on grounding and bonding requirements. However, local codes may have additional or more stringent requirements. Therefore, it is always essential to consult with a qualified electrician or electrical inspector to ensure that your electrical installation complies with all applicable codes and regulations. When installing a service panel, it is crucial to follow the manufacturer's instructions and recommendations. Square D, for example, is a reputable manufacturer of electrical equipment, and their products are designed to meet specific standards and requirements. The hardware that comes with a Square D 5-meter stack may include the ground lug that is intended to be placed under the same screw that attaches the main service bond to the panel. This configuration is designed to ensure a secure and reliable connection between the grounding system and the service panel. However, it is important to carefully review the manufacturer's instructions and consult with a qualified electrician to verify that this configuration is appropriate for your specific installation. It is also important to use the correct size and type of grounding conductors and bonding wires. The size of the grounding conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of grounding conductors based on the size of the service entrance conductors. It is also important to use grounding conductors that are specifically listed for grounding purposes. These conductors are typically green in color and are marked with the word grounding. Bonding wires should also be sized appropriately and should be made of copper or other approved materials. The NEC provides guidance on the size and type of bonding wires that are required for different applications. In addition to proper grounding and bonding, it is also important to ensure that all electrical equipment is properly labeled and identified. This includes labeling the service panel with the voltage and amperage rating of the service, as well as labeling all circuits and overcurrent protection devices. Proper labeling helps to ensure that electrical systems are operated and maintained safely and efficiently. It also makes it easier to troubleshoot electrical problems and to perform necessary repairs. Grounding electrode conductor, often referred to as the GEC, connects the system's grounded conductor, typically the neutral, or the equipment grounding conductor, or both, to a grounding electrode. This electrode, which can be a ground rod, a metal underground water pipe, or a concrete encased electrode, provides a physical connection to the earth. The primary purpose of the GEC is to stabilize the voltage to earth during normal operation and to provide a low impedance path for fault current during an electrical fault. This low impedance path facilitates the quick operation of overcurrent protective devices like circuit breakers or fuses, minimizing the risk of electrical shock and equipment damage. Sizing the GEC is critical and is based on the size of the service entrance conductors. NEC Table 250.66 provides guidance on the appropriate size of the GEC for various sizes of service entrance conductors. For instance, if the service entrance conductors are 2/0 American wire gauge copper, the GEC should be at least 4 American wire gauge copper. The type of grounding electrode also influences the GEC size. For example, if a concrete encased electrode is used, the GEC is typically smaller than if a ground rod is used. The GEC must be continuous, meaning it should not have any splices or joints. If a splice is unavoidable, it must be made using irreversible compression connectors listed for grounding and bonding. The GEC should be securely connected to the grounding electrode using appropriate connectors. For ground rods, listed clamps or connectors are used, while for water pipes, listed grounding clamps that are suitable for direct burial are required. The path of the GEC should be as short and direct as possible. Avoid sharp bends or unnecessary lengths, which can increase impedance. The GEC should be protected from physical damage. If it is exposed to physical damage, it should be installed in conduit or protected by other means. The GEC must be accessible for inspection and maintenance. Avoid concealing it in walls or floors. Regularly inspect the GEC and its connections for corrosion or damage. Replace any damaged components immediately. The equipment grounding conductor, referred to as the EGC, is a critical component of the electrical system that provides a low impedance path for fault current from electrical equipment back to the source. This low impedance path ensures that overcurrent protection devices operate quickly in the event of a fault, minimizing the risk of electrical shock and equipment damage. The primary purpose of the EGC is to provide a safe path for fault current. During a fault, such as a short circuit, current flows through the EGC back to the source, causing the overcurrent protection device to trip and energize the circuit. This prevents dangerous voltage from appearing on the metal parts of equipment, which could cause electrical shock. The EGC also helps to reduce electrical noise and interference. By providing a low impedance path for high-frequency currents, the EGC can minimize the effects of electromagnetic interference, which can disrupt the operation of sensitive electronic equipment. Sizing the EGC is based on the rating of the overcurrent protection device protecting the circuit. NEC Table 250.122 provides guidance on the appropriate size of the EGC for various overcurrent protection device ratings. For instance, if the overcurrent protection device is rated at 20 amps, the EGC should be at least 12 American wire gauge copper. The EGC can be a wire, a metal raceway, or other approved conductor. When using a wire as the EGC, it should be green or green with yellow stripes to clearly identify it as a grounding conductor. The EGC should be continuous and securely connected to all metal parts of electrical equipment that are likely to become energized during a fault. This includes enclosures, motor frames, and other conductive parts. The EGC should be connected to the equipment grounding bus in the panel board. This bus is typically bonded to the neutral bus of the service entrance, providing a direct path for fault current back to the source. The EGC should be protected from physical damage. If it is exposed to physical damage, it should be installed in conduit or protected by other means. Regularly inspect the EGC and its connections for corrosion or damage. Replace any damaged components immediately. Bonding is the process of connecting non-current carrying metal parts of electrical equipment and systems together to create an electrically conductive path. This path ensures that all metal parts are at the same electrical potential, minimizing the risk of electrical shock. The primary purpose of bonding is to reduce the risk of electrical shock. By connecting all metal parts together, bonding ensures that there are no voltage differences between them. This prevents dangerous touch voltages from appearing on equipment, which could cause electrical shock. Bonding also helps to reduce electrical noise and interference. By providing a low impedance path for high-frequency currents, bonding can minimize the effects of electromagnetic interference, which can disrupt the operation of sensitive electronic equipment. Bonding is required for all metal parts of electrical equipment and systems that are likely to become energized. This includes enclosures, raceways, pipes, and other conductive parts. Bonding can be achieved using various methods, including bonding jumpers, bonding bushings, and bonding locknuts. Bonding jumpers are used to connect metal parts together that are not already electrically connected. Bonding bushings are used to bond metal conduit to enclosures. Bonding locknuts are used to bond metal boxes to enclosures. Bonding connections should be made using approved connectors and methods. The connections should be tight and corrosion resistant to ensure a reliable electrical path. Regularly inspect bonding connections for corrosion or damage. Replace any damaged components immediately. Grounding and bonding are essential for electrical safety. They protect people from electrical shock and reduce the risk of fire and equipment damage. Grounding provides a path for fault current to flow back to the source, causing overcurrent protection devices to operate. Bonding ensures that all metal parts are at the same electrical potential, minimizing the risk of electrical shock. Grounding and bonding are required by electrical codes and standards. The NEC provides comprehensive guidance on grounding and bonding requirements. The purpose of grounding is primarily about safety and protection, not about making the electrical system function. In simpler terms, grounding is like having a designated escape route for electricity in case something goes wrong. It is designed to minimize the risk of electrical shock, fire, and equipment damage. The ground provides a low-resistance path for electricity to flow back to the source in the event of a fault, such as a short circuit or insulation failure. This low-resistance path allows a large amount of current to flow quickly, which trips a circuit breaker or blows a fuse, cutting off the power and preventing further damage or injury. The grounding system also helps to stabilize voltage levels in the electrical system. It provides a reference point for voltage, which helps to prevent voltage fluctuations that can damage equipment. Grounding also helps to reduce electrical noise and interference. By providing a low impedance path for high-frequency currents, the grounding system can minimize the effects of electromagnetic interference, which can disrupt the operation of sensitive electronic equipment. There are several different types of grounding systems, including system grounding, equipment grounding, and static grounding. System grounding involves connecting the neutral point of the electrical system to earth. This helps to stabilize voltage levels and provides a low resistance path for fault current. Equipment grounding involves connecting the metal parts of electrical equipment to earth. This prevents dangerous voltages from appearing on the equipment in the event of a fault. Static grounding involves connecting objects to earth to dissipate static electricity. This is important in environments where static electricity can cause explosions or damage sensitive electronic equipment. Grounding is typically achieved by connecting a grounding conductor to a grounding electrode, which is a metal rod or plate that is buried in the earth. The grounding conductor provides a path for electricity to flow to the earth in the event of a fault. Bonding, on the other hand, is the practice of connecting all metal parts of an electrical system together to create a continuous electrical path. This is done to ensure that all metal parts are at the same electrical potential, which reduces the risk of electrical shock. Bonding is typically achieved by using bonding jumpers, which are short lengths of wire that connect metal parts together. Bonding is required for all metal parts of an electrical system, including metal conduits, metal enclosures, and metal equipment. Proper grounding and bonding are essential for electrical safety. They protect people from electrical shock and reduce the risk of fire and equipment damage. Therefore, it is important to ensure that all electrical systems are properly grounded and bonded in accordance with electrical codes and standards. For example, in a typical residential electrical system, the neutral wire from the utility transformer is connected to a grounding electrode at the service entrance. This connection is called the system ground. In addition, all metal parts of the electrical system, such as metal conduits, metal enclosures, and metal equipment, are bonded together using bonding jumpers. This creates a continuous electrical path that helps to prevent electrical shock. In an industrial setting, grounding and bonding are even more critical. Industrial electrical systems often operate at higher voltages and currents than residential systems, which means that the risk of electrical shock is greater. In addition, industrial environments often contain flammable materials, which means that the risk of fire is also greater. Therefore, it is important to ensure that all industrial electrical systems are properly grounded and bonded in accordance with electrical codes and standards. Some additional points to consider include the grounding electrode should be installed in a location where it will be in contact with moist soil. The grounding electrode should be protected from physical damage. The grounding conductor should be sized appropriately for the size of the electrical system. Bonding jumpers should be sized appropriately for the size of the electrical system. All grounding and bonding connections should be made using approved connectors and methods. All grounding and bonding connections should be inspected regularly for corrosion or damage. If any corrosion or damage is found, the connection should be repaired or replaced immediately. It is also important to note that electrical codes and standards are constantly evolving. Therefore, it is important to stay up to date on the latest requirements for grounding and bonding. By following these guidelines, you can help to ensure that your electrical system is safe and reliable. Remember that electrical work can be dangerous. If you are not comfortable working with electricity, it is best to hire a qualified electrician.